Hello learners, I welcome you to this introductory lecture on CFD. In this particular lecture, I will be essentially discussing about this question, why CFD should be studied and what is its practical importance in the engineering applications. Although this is my primary objective, I would like to deal with the question, what is CFD before I go into why CFD. So yes, the CFD stands for computational fluid dynamics. As it is shown here, it is essentially a branch of fluid mechanics that models the flow of fluids such as liquids, gases and plasmas using computers. You will be essentially using computers here for the fluid mechanics principle. Especially in fluid mechanics, you will have an important branch called fluid dynamics. Fluid dynamics will be dealing with the flow of fluids at large. Most of the engineering problems will be dependent on the principles of fluid dynamics. The principles may include the continuity equation, the momentum equation, the energy equations. Like that, many mathematical expressions that you take in fluid dynamics will give a mathematical form to the engineering problems. Given the mathematical form, you combine that mathematical form with the computational power that will give you a wonderful solutions at the end. So what you're essentially doing is you are combining the computational power with the principles of fluid dynamics here. So essentially, fluid dynamics principles will be dealt along with the computational power. So as these are dealt together, that will give you a very practical solutions to the real world engineering problems. So that's what CFD does in nutshell. Along with the CFD principles, along with this fluid dynamics principle, you will also have heat flow here. That the heat transfer is also an important subject that you study for engineering applications. Most of the times the principles of heat transfer are more or less analogous to the principles of fluid dynamics. So what you can do is you can apply whatever the principle that you have studied for fluid dynamics even for the heat transfer, because there are many analogous things to heat transfer and fluid dynamics. Let's say if you take fluid dynamics, you will have something called as a boundary layer there, right? So that you call it as velocity boundary layer. Similarly, in heat transfer, you will have something called as a thermal boundary layer forming. So such analogous terms are there, such analogous behavior is also there. To let you know what is analogous behavior of the fluid mechanics and this heat transfer, let me give you an example. What is the driving force for the fluid mechanics? Let me change this. I'm speaking about the driving force. The driving force in fluid mechanics or for the fluid flow, on the other side heat flow. The driving force for the fluid flow is pressure, P-R-E-S-S-U-R-E, pressure difference. And on the other side you have heat flow, which will come into the play due to the temperature difference. From high pressure region to the low pressure regions, fluids flow automatically. From high temperature region to low temperature region, heat flows automatically. These are the natural principles, you know, right? So the driving force is essentially having an analogous nature here. So most of the times the principles that you have in CFD will also be applicable for computational heat flow as well. So to perform these simulations also, you will be dealing with the principles of CFD. That's all about what is CFD. Moving on to the question, why CFD? Let me put the things in perspective. To put the things in perspective, let me tell you the story of testing an air vehicle. You might be knowing this famous social media trend then and now. People are doing this stuff a lot these days on social media. Similar kind of stuff also here. If I have to test an aeroplane or an aircraft in the olden days, people used to send the first, what I should say, prototype in unmanned manner. That is, they will be sending this particular aeroplane without human in it, and if it works well and reasonably well, then they will go with a trained dog. They will use a trained dog to test it again. Then in the third phase, they will be using a person, and this person will be given huge safety precautions, with huge safety precautions like fire safety is taken care. He will be given so many parachutes to fly back to the land if something fails in the air. And then after so many trial and errors in this fashion, using lot of material and lot of time, people used to finally test and certify given aircraft or an aeroplane. That used to be the story in the previous days. But later, what happened? You have CFD coming into the play. When CFD came into the play, the scenario changed a lot. Even in the first flight of an given aircraft or an aeroplane, people are coming forward, or I should say they are daring enough to have people like presidents of a nation, prime ministers of the nations, army officials of the nations going on board within the first flight itself. So how could they have reached this level of confidence in their testing? It is because they could test their prototypes at the simulation level using the principles of CFD. There might be a little bit of exaggeration in this story. Take it with a pinch of salt. Take it with a pinch of salt. But the story gives us a very good perspective of how CFD has changed the story of designing an aircraft or testing an aircraft. So this has a huge impact on the way engineering is done when it comes to the fluid dynamic principles. Moving on, this is what I have got from Google. I have pressed CFD and then I've got all these images there. In the images section, you can also get the same stuff here. You can see CFD applied to the car here. There are many cars here. Here also you have car, here also you have car, here also you have car. This is also a kind of formula racing car. This is a car, this is a car. So if you have to design a best design, a best aerodynamic design, I should say, when it comes to aerodynamic design, means it is the shape of the car that you are deciding here. Okay. So what kind of drag it will have, what kind of lift it is having, is designed based on the principles of CFD again. So before you actually create your car, you can actually test what happens to that if it is used in a real-time scenario at so and so speed, how it will behave. Okay, one of the important things that you should take care while you are designing a car is you should take care that it won't fly, right? It should not fly, it should stay on the ground. Okay, if the lift is higher than the drag, it will obviously fly in the air. So what you should take care, you should always take care of the drag properly. The lift and drag ratio should be maintained such a way that there will not be any flying of the car. At the same time, you will have the reverse scenario when you design flights here. You can see flight here, you can see kind of aircraft here. You can see this is also an aerofoil shape that you have taken for this wing of an airplane. So that comes under the aerodynamic design as well. So here lift should be more and the drag should be less. How will you ensure it? In the design phase, using the principles of CFD. Even in the recent days, people are sending rockets, right? Rockets into the space. NASA is sending, ISRO is sending. How they are able to send that? They are able to send it using the principles of simulation and the CFD again. Here you can see a wind turbine. Here you can see various components of the engineering devices, how the flow is happening in all these cases. You can definitely see here. This is a kind of turbine. I guess this is a Francis turbine. So likewise, many engineering devices have changed the way, the CFD has changed the way how all these engineering devices are designed with much effectiveness and much efficiency, that too at a very reduced cost of testing. So that's the beauty of CFD. Moving on, what CFD does is it bridges the gap between the pure theory and pure experiment. So people, before the advent of CFD, they were not able to correlate the principles that are available in the theory with the principles that are available in the experiment. So there is a lot of gap that was there between the theory and the experiment, and this has been efficiently bridged with the advent of computational fluid dynamics. Essentially, after the advent of high power computing, when supercomputers which can handle very high amount of computational power has come in around 1960s and 1970s, CFD has changed the way the aircrafts are designed. So then on, CFD is being applied in various fields like rocketry, design of cars and vehicles, and even buses, and even ships, naval applications. All these things are changed in a phenomenal manner with the advent of CFD. So CFD has a major role in the way the engineering applications are designed. This is especially when there is a fluid being involved in that particular engineering applications. CFD will have a lion's share in the design of that particular engineering equipment. So put together, CFD will be giving you a very wonderful bridge between your theory and the experiment. It will essentially bridge these two to give you a real-time solution at the design level without actually going for the real-time prototypes. That's the beauty of your computational fluid dynamics. So put together, you will come to the point of benefits of CFD. So the first one being, it will help you in faster decision making. You can take the decision at a faster rate, because previously what people have to do, they have to do all the physical testing and then make sure that device is functioning very well. Then you can go for the final decision making. Whereas CFD, you need not actually do all that testing. You can do all the testing using computers itself. So you're getting the solution within the computer, which is so reliable. So that will help you in accelerated decision making. And in the process, what happens is the development time is significantly reduced. You need not actually go buy the equipment. You need to assemble it, test it. You need to spend a lot of money as well. So you have reduced the cost, and you will also reduce the labor as well. So that is one more benefit. And even you can test the complex scenarios. Okay, when it comes to the complex scenarios, like I given the example of aircraft testing, is really a complex scenario. You can actually you have to actually go into the air, send your person, and you're putting the life of that person at a risk. Means it's not a simple thing. It is so complex. So that complex scenario can also be dealt at a testing level in the simulation of CFD. And not just the complexity that involves with the human life, it also the complexity that involves with the engineering problems that can also be tested with the principles of CFD. And moving on, it will give you something called as a sustainable testing. Okay, what is sustainable testing means? You will have so many regulations that are, you know, proposed by various government agencies, and even UN is coming with certain, regulations that needs to be fulfilled before you actually release your product into the market. So what are these sustainable principles? Sustainability will essentially reduce the cost and improve the impact. How can you get the improved impact with the reduced cost? When you can test the things in an simulated manner without doing the actual physical testing. You are doing the testing in a simulated manner, so obviously you'll be able to reduce the cost and improve the impact. So that's how you will be able to meet the regulation, and you will also improve the impact. That's what the sustainable testing means. So CFD is actually helping you to do all that. Moving on, we have one more benefit of CFD, that is, it will give you something called as a accelerated time to market. At the end of the day, if you produce any given product, you have to market it. Okay, in order to market it at accelerated time. Okay, if you don't market the given product on time, you will not have that value to that particular product. In order to have the value to that product, you need principles of CFD. So it has essentially improved the market value of the products. Also, CFD has improved innovation and design flexibility. The design can be tested very easily. You can do trial and error. You can change a given aspect, you can change a given geometry, you can change given parameter very easily at a computer level. With the click of a button, you can actually change whatever the parameter you want to change, whatever the geometry you want to change. You will be keep changing and keep trying various stuff that will give you an innovation. The innovation will obviously improve, will get enhanced because of this click of a button. With a click of a button, you can get the results. That's the beauty of CFD. And also it will help you in improved collaborations and knowledge sharing. You can easily share the engineering principles with the fellow beings across the world who are interested in that particular field. And it also essentially leads to the scalability and adaptability. Whatever the big product that you have created, aircraft, that if you have to reduce it down to a small thing, people like CMs and all, they don't need a big aircraft. They can have a small aircraft. If you have to reduce that to a smaller size using the same principles, you can do with the principles of CFD. And sometimes you have designed it for the small things and you have to increase it or enhance it to the bigger scale. That can also be done with the principles of CFD. So essentially what you're doing is you can increase the scale of it and you can decrease the scale of it. Also, you can adapt it to the situation. Okay, in the given situation, the size may be required, can be small, the size required can be big. Depends on the situation. You can adapt your solutions from one form to the other form very easily. That's the benefit of CFD. So put together, these are the benefits of CFD. So I hope you got a clear idea on why CFD should be studied. I thank you for joining. Thank you.